In the previous videos, we introduced the concept of dimensions of a vector. We talked about vector being in one dimension, it can also be in two dimensions or in three dimensions, alright? It was stated that one-dimensional vector is just a line with arrowhead showing the direction. Two-dimensional vector is a vector in plane, so you could have the xy plane as standard majorly, but you could also represent it as xz or yz plane. Then when a vector is in three dimensions, we say that the vector is in space. So it has three coordinates, the x, the y, and the z. The z represent the altitude, the height. Is that okay? Now, we looked at certain forms of formula we need in order to handle the algebra of these vectors in different dimensions. On the board here, we want to apply the formulas that we established in our previous video. So we start with this question on the board, please. I welcome you to come with me. Let's read this question together and then solve it together to see. Are you ready? Let's go. A mouse pointer on the display of a computer is initially at a point 6.0 centimeter, 1.6 centimeter. You know, this is like x, y. Are you getting me right? X, y. So x value is this, y coordinate is this, okay? With respect to the lower left corner, that's lower left side corner, of course, of the computer screen. If the pointer is moved to an icon located at a point 2.0 centimeter, 4.5 centimeter, what is the 1. Displacement vector of the pointer, 2. The magnitude of the displacement vector of the pointer, and 3. The direction of the displacement vector. So how do we solve this problem? It's a simple one, okay? We have 2 points on the computer screen. Initially, the mouse pointer is at the lower left side corner of the screen, and they give us the coordinates of that point to locate where the pointer is specifically in the computer screen is at point 6.0 centimeter, 1.6 centimeter. So you can actually locate it considering the x and y coordinate. And then the pointer was moved to an icon, okay? You know, your computer screen have icons everywhere. So the icon is at the position located by this coordinates 2 centimeter, 4.5 centimeter. So in getting the displacement vector, the first part of the question, first we need to take note of these positions, and then remember that displacement is simply change in position. What did I say? Change in position. Usually the final position minus what? The initial position. Remember that the initial position of the pointer is point A. I've decided to call it point A, and then the final position is what? Point B. So to get the displacement, we'll be talking about B minus what? A. And you know, to add or subtract vectors, you handle them component by component. So it's going to be x to x, y to y, z to z. Here we have only 2 coordinates. This is a vector in plane. Is that okay? 2-dimensional vectors. So x and y. So we're going to do the final x minus initial x position, and then the final y position from B minus initial y position in A. And that gives us the displacement, alright? So let us see. Permit me to use this as our displacement vector for the pointer. So it's going to be the final position B minus the initial position A. If I want to put O, I can say, okay, let this be OB and then minus OA. Where O is just too rigid, let me fix it up, okay? But I can still simply say B minus A. That OB, O there represent the origin, and the origin has the coordinate 0, 0. When you have OB, it simply means point B minus point O, minus point of the origin. Like I said, the origin is usually 0, 0. So even if you do B minus O, you still get your B. If you do A minus O, you still get your what? A. So eventually, even if I write OB minus OA, it's the same as B minus A, the final minus what? The initial. Are you ready? So we go ahead, and then this is going to give us, our point B is given with the coordinates 2.0, 4.5 centimeter, and then that is minus OA. Our point A is 6.0, and then 1.6. Good. So the displacement vector is now going to be, let's do the subtraction and see. Alright, think of 2 minus 6. We are going x coordinate minus x coordinate. Is that okay? When the point is given to you, usually we use this. A point in the Cartesian or rectangular coordinate is defined, let's say point P, by these 2 coordinates x, y. I want to believe that this point Based on what we've explained from previous video, you already are used to this concept of rectangular or Cartesian coordinate. So let's go. The final x position in point B minus the initial x position in point A. 2 minus 6 is going to give us minus 4 centimeter. Is that okay? Remember x to x, y to y, then z to z if you have up to 3 coordinates. Then 4.5 minus 1.6 is going to give us about 2, I think 2.9, right? So you can find out 2.9. That's what you're going to get. 4.5 minus 1.6, 2.9 cm. Alright, so this is the coordinate of the displacement vector. Scalars. They are scalars because these are just numbers. Is that not so? I can leave my answer like this. If it is an objective exam, depending on how the options are presented, you can leave your answer like this. But again, I'd like to convert it to full vector form. Is that okay? The displacement vector in terms of vector form, because these are scalar components of the displacement vector. Scalar component. Let's now put it in full vector form. It's going to be minus 4i. You see, I'm introducing the direction vectors, the unit vectors, ij as the case might be, added to this 2.9, which is y-axis. It has the j direction. Of course, we've gotten the displacement vector of the mouse pointer. I'll be taking a short break. When we're back, we'll look at the magnitude and direction of the displacement vector. Of course, you should be thinking of the Pythagoras rule and as well as the tan inverse of the vertical divided by the horizontal component of the vector. You are welcome from the short break. Now I want to look at the second and third part of this question. I want to get the magnitude of the displacement vector of the pointer and of course the direction. But when we solved the first part of the question before the break, we obtained the displacement vector. Recall, we obtained the displacement vector to be minus 4i plus 2.9j. This was the displacement vector. How do we get a magnitude? To obtain a magnitude of displacement vector, we use Pythagoras theorem. It's an absolute value, so the final answer you will get will always be positive. Don't forget that. The magnitude, the length, the absolute value, the modulus of any quantity is always positive. That being the case, all I need to do is to substitute. In place of this x, I will put this minus 4 and then I will square it. But I don't have, if I choose not to put a minus, I commit no crime. I commit no crime. I've already stated the reason. Magnitude is always positive. Is that okay? And even apart from that, if you fix in this minus 4 and then you square it, that minus 4 squared, the square would remove the negative. It will become positive 16. So take note of that, please. Plus 2.9 and then squared. You'd see that the magnitude of the displacement vector will now be what? Let's find out. If you punch this in your calculator, square root of 4 squared plus 2.9r squared, then you close the brackets. Alright, so it's giving me 4.9 centimeter. So this is the magnitude of the displacement vector of the mouse pointer. This time around, I want to look at the direction. Want to look at the direction. Now, how do we obtain the direction of this vector? Please, let us quickly look at this on the board. I'm going to sketch it because to get the direction of a vector is very important that we'll understand the concept. There is something that is called the Argand diagram, actually encountered under complex number in the study of mathematics. It helps us to locate the position or the quadrant in which a particular quantity is located. This displacement vector, if you look at, this is positive y-axis, this is positive x-axis, this is negative y-axis, this is negative x-axis. Now the displacement vector, our x value is minus 4, which means it is somewhere here. Let me locate it in minus 4, for example, minus 4. Alright, this is the origin, 0, we know that. Then the y component is positive 2.9. Let me locate here as 2.9. Do you take note that if you trace up this point to locate your displacement vector, it's going to be here? Does that make sense? So the displacement vector, if I join it to the origin, Good. This is the R, the displacement vector R. Now, this displacement vector made an angle theta with negative x-axis. So, if we calculate this negative x-axis, the actual direction of this displacement vector is that measured from positive x-axis anti-clockwise down to the vector, then you stop. I repeat that again. The direction of a vector, I stated it in one of our previous videos. Direction of a vector is conveniently measured from positive x-axis in an anti-clockwise direction, in a counter-clockwise direction, down to the vector itself. So the real direction of the vector, let's represent it as alpha. Is that okay? Alpha is equal to the direction of the vector. Direction of vector. In fact, it is only when this displacement vector is in the first quadrant, because this is first quadrant, second quadrant, third quadrant, and fourth quadrant. It's only when this displacement vector is in the first quadrant. That is when, if you calculate theta directly and you get the value of theta, you can now say that is the direction. Apart from that, if the displacement vector is in the second, in the third, or in the fourth quadrant, please always remember, whenever you calculate theta, you have to measure the angle of the vector from positive x-axis down to the vector itself. Then do some form of plus or minus, as the case might be, either using 180 degrees, 270 degrees, or 360 degrees. Is that okay? Alright, now let us do this. The first thing I will do is to get theta, because theta directly is tan inverse of y all over x, which of course is going to give us tan inverse of the y value is 2.9 all over the x value is 4. You see, I don't have any business with that negative sign. This negative sign here, I don't need it for calculating this theta, this angle. The essence, the reason for this negative, the effect is simply to tell us the position, the quadrant where the displacement vector is located. Simple. And from what I sketched here, I've already shown you. Is that okay? So we don't have any need for that. So if we do that, theta is going to give us, let's find out please, tan inverse 2.9 all over 4 in brackets. Okay, so it's giving me 35.9 degrees. 35.9 degrees. This is not the actual direction of the vector because the vector is not in the first quadrant. Look at it in the second quadrant. So to get this alpha now, the direction alpha will now be the direction of the displacement vector. The direction of this, which is alpha, as I showed you from the sketch, is now equal to, take note, from positive x-axis to negative x-axis is 180 degrees. 180 degrees is a semicircle. Is that okay? Now out of it you know theta, which is 35.9 degrees. You are left with just this portion from this positive x-axis down to what? To the vector itself, which is alpha. So to get the value is going to be 180 degrees minus the 35.9 degrees. And if you do that, the direction is now equal to, if you subtract 180 minus 35, it's going to give us, right, that's 144.1 degrees. So this is the direction of the displacement vector. Alright, take note of this and please be watchful because we'll still make use of this concept in our subsequent video when we treat our Gantt diagram in mathematics. Now we have this question number 2 on the board, okay? Let us look at the question together. It's an interesting one. 3 force vectors ABC in a plane have magnitude 10 Newton, 7 Newton, and 8 Newton respectively, and their respective angles with the horizontal direction are alpha equal to 35 degrees, beta equal to minus 110 degrees, and gamma equal to 30 degrees. Find the magnitude of the vector S equal to A minus 3B plus C. How do we approach this question? You want to take note that in the question here, we're given 3 vectors, their magnitudes were given to us, and the angle they made with the horizontal. Since they just mentioned horizontal, they didn't mention anything about negative, just say horizontal, it means it is the positive x-axis. Now, their respective angles were given to us. Can we take our mind back a little to what we did when I introduced the concept of polar coordinate of a vector? You have the Cartesian coordinate and the polar coordinate. Now, the polar coordinate deals with the magnitude of the vector as well as the angle that the vector made with the positive x-axis. Do you remember that, right? And I told you that for us to get the x and y component from this polar form, we can do r cos theta and r sin theta respectively. Quickly take your mind back. You can also watch our previous videos to remind yourself of that. Now, for us to be able to obtain this, we must convert this ABC from their polar, because these values given to us are polar coordinate values. Magnitude of the vector and the angle it made. They are polar coordinate values. So we need to convert them to rectangular, to Cartesian coordinate. We need to get the x and y component of each of these four vectors. Then we will now substitute it here. So let me write. It implies that s, which is equal to a, will now give us something like axi plus ayj. Is that okay? Then minus 3 open bracket bxi plus byj. Then plus, we'll come to c, cxi plus cyj. So this is just what we need for this question. Get the rectangular coordinates, the Cartesian coordinates, from the polar coordinate value given to us. Is that okay? And then substitute here. That will now allow you to do plus and minus of the vectors as the case may be. But before we go into this question fully, can I show you something, right? This thing has been put in a word problem format. This question is actually like giving something like this. Let's assume that you have your x and y coordinates. This is the origin, point 0. Is that okay? So this is positive y, then x, positive, and then negative y and negative x. Now, looking at what we're given, the first vector A has magnitude of 10 Newton and it is 35 degrees from the horizontal. So it's just like this. From this horizontal, let me measure up to this and say this is 35, for example. So this is the first vector A, whose magnitude is equal to what given to us? 10 Newton. Alright, so I'm just doing this to give a full interpretation to this question for you. 35 degrees. 35 degrees. Then the next one, B, is 7 Newton with an angle of 110 degrees, although they gave us negative there, but that doesn't matter. All we know is 110 degrees, it goes this way. Are you seeing that, right? It goes this way, we can fix it up here. So this is our B, which is equal to 7 Newton. They are false vectors. We can use F1, F2, and F3 to represent that. Just that the question gave it to us in terms of ABC. Then the last one is what? The last one, how many degrees? C. 30 degrees with the horizontal. Which means I will come over here, okay, and then maybe I'll draw something like this. Let me use red marker to superimpose it in this. 30 degrees will go this way. Is that not so? So, this is going to be 30 degrees. Then this vector C there. So I have ABC, and of course the magnitude of the vector is 8 Newton. So this is actually the sketch of that question. Is that okay? Now we're going to take a short break. When we come back from the short break, we'll obtain the rectangular Cartesian coordinate value of ABC, and then substitute here, simplify, and get the displacement vector S, whose magnitude we are asked to get. You're welcome from the short break. Now we're going to obtain the rectangular coordinate, the Cartesian coordinate of ABC. Now, is that okay? So let us start with A. Remember, we already established that if you're given the polar coordinate of vectors, you can get the x coordinate of that vector using magnitude of that given vector cos theta. And then you can get the y coordinate using magnitude of that vector sin theta. So let us apply that principle to this now. So I want to get, starting from A, is that okay? The AX coordinate is going to be magnitude of A. Magnitude of A, let me show for the first one, then the others will just cos the angle that A made, which is 35, alpha. Magnitude of A is 10 Newton, cos alpha is 35 degrees. So Let us see what this is going to give to us. Is that okay? If you work it out, you're going to get 8.19 Newton. Let's move on to AY. That's going to be magnitude of A, then sine alpha, which of course is 10 sine 35. 10 sine 35 is going to give us what? 10 sine 35, let's find out. 10 sine 35 is going to give us 5.74 Newton. We can now move on to obtain Bx and By. But before Bx and By, can we get the displacement vector A in terms of Axi and then Ayj? So Axi plus Ayj is now equal to, let's see what it's going to get. I'll be using red marker for that. So that is going to be 8.19I then plus 5.74J. That's the X and Y component. Also, we'll do for B. So we're going to have Bx, which is magnitude of B cos the angle that B made. And the angle that B made is beta. Is that okay? If you work on that, you're going to get magnitude of B from the question is 7 Newton. Cos beta, that is cos minus 110 degrees. So let's see what we get from here. We are working on Bx. Is that okay? That is 7 cos, open bracket, minus 1110. That is minus 2.39. Minus 2.39 Newton. Then we obtain for the y component of B, which is magnitude of B sine beta. Of course, that's going to be 7 sine minus 110. Let's work it out and see. 7 sine, open bracket, minus 110. So that's giving us minus 6.58. 6.58 Newton. Once again, we can write the displacement vector for B, which of course will be Bxi plus Byj. Now, where is our Bxi? Our Bx is minus 2.39i, then it's meant to be plus the By value, and the By value is minus. So the minus will change that plus to minus 6.58j. Similarly, for C, we get for Cx will be magnitude of C cos gamma, because C makes the angle gamma with the horizontal. That's going to be, the magnitude of C is 8. 8 cos gamma, that is cos 30. If you work in this, let's see what we're going to get. So 8 times cos 30 is 6.93. 6.93 Newton. And then Cy will give us magnitude of C sine gamma, which will be equal to, right, magnitude of C sine gamma. The magnitude of C is what? 8. Then sine 30. Of course, if you work on this and tell you, of course, it's 0.5, let's say have that at heart. So multiply by 8, you get 4 Newton. Alright, so what's going to be the magnitude, or the displacement vector of C rather? The displacement vector of C, which is Cxi plus Cyj, will now be equal to, what is our Cx value? 6.93. So it's going to be 6.93i, then plus 4j. Okay, so take note of this. Take note of this. These are the displacement vectors. I'm sorry I didn't write this in a red marker, so let me underline them. Is that okay? And then take note of this as well too. Once again, we'll go on a short break. When we come back, we'll now round off. Having obtained this component, we'll now substitute and simplify to get our displacement vector x. And once we obtain that displacement vector s, we can be able to calculate the magnitude. You are welcome from the short break once again. Before the break, we obtained the rectangular coordinate, the Cartesian coordinate of displacement vector ABC from their polar coordinate values given to us. You know that this rectangular coordinate would allow us to add or subtract similar components, is that not so? Which is, of course, what this is asking us to find. to get the displacement vector of S and of course get the magnitude. Now we are going to rewrite the displacement vector S in terms of its coordinate using the value we have here, and it's equal to A. The rectangular coordinate of A is 8.19i plus 5.73j minus 3 times displacement vector B, which is minus 2.39i minus 6.58j, and this is to be added to vector C plus displacement vector C, which is 6.93i plus 4j. So to obtain the displacement vector S, all we need to do, remember, when you are adding or subtracting vectors in either 2 or 3 dimensions, you add a component, the same components together. So we're going to add the XX component together, those bearing II, and then the YY component, those bearing the direction vector J there. Is that okay? So let us do that and see. 8.19, that's going to be minus 3 times minus 2.39. You know, this minus will open up this bracket, and if this negative sign opens this bracket, the signs inside the bracket will change. Is that okay? So this minus become plus, this minus also become plus. So that's going to be minus 3 times minus 2.39 will now change to plus 3 times that value. So plus 3 times 2.39. Good. Added to the x component of this, which is 6.93. So from here, it's giving me 22.29i. Go back again and do same for the y component. So that's going to be 5.73. Then come over here again, minus 3 times minus 6.53. Of course, you need to change to plus, minus minus to give you plus. That's minus times minus. So plus 3 times, use the multiply the y component, 6.58. 6.58. Close, and then we're going to add it to the y component of vector C, which is 4. This gave me plus 29, that's 29.47j. Good. We can now obtain the magnitude of S. This is displacement vector S. So for this question, if we're asked to get the displacement vector, this is where we stop. That is displacement vector of this S. We'll stop here. Is that okay? So if I let me indicate it, displacement vector S, displacement vector S. Good. So take note. Now to get the magnitude, for magnitude of S, this will now give us the Pythagoras rule, square root this term. So it's going to be 22.29 squared. All right, you know this is affecting all the terms here, and then 29.47 squared. So let us see what this is going to give to us. We are working on this, so it's going to be square root. Now I'm going to press it at once in the calculator. Square root, open bracket, open under bracket, 22.29, close the bracket, and then raise to power 2. I'm going to add it to open under bracket to have 29.47, close that bracket, raise to power 2, then close everything finally because of the double bracket we started. So this is 36.95 Newton. This is the displacement vector's magnitude S we are asked to find, and that's the solution of the problem on the board.